am Dr. Nitisha Shrivastava. Welcome to the control system lectures. Now, in this lecture, we will see that what are the time domain specifications as related to a unit step response. The transient portion of the time response is the part that goes to 0 as time becomes large, that is time reaching infinity. Nevertheless, the transient response of a control system is necessarily important, since both the amplitude and the time duration should be kept under limits. And for a linear control system, the characteristics or the time domain specifications of a second order system is of great importance. Here we will understand how the limits of the output response should be under the control. The response of a control system, when the input is a unit step function, and then it is known as a unit step response. So, this is a typical unit step response. As we had seen, the value of damping ratio zeta. When zeta is equal to 1, the condition is of critical damping, and when zeta is equal to 0, it is the case of 0 damping. However, most of the control systems are designed for the damping ratio ranging between 0 and 1. So, the typical output response of a second order system when subjected to a damping ratio which is between 0 and 1 has oscillations which damp out. Now, there is a specification, there would be a specification that what would be the limit of the overshoot and undershoot. Now, it is also expected that the overshoot does not go very high. So, this is the time domain specifications. Now, this is the particular graph. This graph is for the value of zeta, which is lying between 0 and 1, because most of the control systems are designed with damping in the range between 0 and 1. So, this is the typical response starting from 0, having the first overshoot. This is the first overshoot because the unit step response is 1, that is we are talking because it is a step response and the unit step response 1. Therefore, this is the line which gives us the reference input r of t. Since from the time 0, the response curve reaches the first overshoot at the time t p. This distance from 0 till the time that the graph reaches, the response reaches the first overshoot is termed as the peak time, written as t p, and the value of the response, that is the peak overshoot. This is the first peak overshoot, the distance from the reference input 1 till m p, this first overshoot is known as the peak overshoot or the maximum peak which the graph will attain, and that is the first overshoot. After that, the oscillations damp out. So, this value is the peak overshoot. Then what is rise time? Rise time is the time when the C of t response reaches unity for the first time. So, that is the rise time, and delay time is when the response of the curve is 50%, that is at the value of 0.5. The definitions here, this is the allowable tolerance value with the dotted line, this is the time axis, and this is the response C of t. So, according to the definitions, what is a delay time? Delay time is the time required for the response to reach 50% of its final value. This is T d, time response T d. For the rise time, this is T r, sorry, this is the rise time T r, and this is the peak time T p. Rise time, it is the time required for the response to rise from 10% to 90% of the 90% of the final value for overdamped systems and 0 to 100% of the value for the underdamped systems. Underdamped systems are systems whose damping ratio is lying between the range of 0 and 1. For that it is 0 to 100%. Peak time is the time required for the response to reach the peak time or the peak overshoot. This is the peak time T_p when the value of the response is first overshoot. And what is peak overshoot? It indicates the normalized difference between the time response peak and the steady state output. This is Ctp minus C infinity, that is when the time reaches infinity, that is the steady state value multiplied by 100. Settling time is the time required for the response to reach and stay within a specified tolerance band. Usually the tolerance band is 2% to 5% of the final value. And what is steady state error? It indicates the difference between the actual output and the desired output, and it is represented by ESS. This is the tolerance limit here. So, as we defined, what is rise time? Rise time is obtained when C of t reaches unity for the first time, as mentioned here, where rise time is Tr, the distance from here to here, this distance when the graph reaches unity. So, this distance is Tr. So, what is the expression for the rise time? The expression for rise time is, we have to use the relation that when the response reaches unity, as we had seen that this is the time response of a unit input, unit step input, and the value here is 1 and 1 minus gets cancelled out. So, we get this equation which is equal to 0. That means that we are remaining with this term sin omega and root of 1 minus zeta square Tr, since we are talking about the rise time which is equal to 1, that is known as the rise time. Therefore, we have put the value Tr here. And what is the acceptable solution for this? The acceptable solution is that this value should be equal to pi, and therefore, the time response curve when it reaches infinite, when it reaches 1, that is rise time is pi, and this part, that is tan inverse root of 1 minus zeta square by zeta upon omega n root of 1 minus zeta square. So, this is the rise time, that is when the response reaches unity, and this is obtained by equating the response to unity and thus expression for the rise time. What is peak time? As we can see here, peak time is when we reach the first overshoot. These oscillations, because the damping ratio is this response is for the damping ratio lying between 0 and 1, and therefore, the peak time is obtained by the relation dCt by dt, and when you differentiate the C of t, the expression C of t is the unit step response of a second order system. It is differentiated since we want the maximum value of the curve. Our curve has a response which is oscillating. We want the maximum value of the response, and therefore, we differentiate the C of t value, that is the time response of a unit step response second order system, and equate the value to 0. Since we are asking for a value which is maximum of the overall response. So, when you differentiate C of t, we get the expression minus this value and equating it to 0, since we want a maximum value. So, manipulating the terms here, we are having a term root of 1 minus zeta square, as also discussed during a second order system. Here we can see that if this is phi and this is root of 1 minus zeta square, this is zeta and this is 1, then what would be sin phi? This is sin phi, and therefore, cos phi from this is simply zeta upon 1 and correspondingly tan phi. So, substituting root of 1 minus zeta square as phi, we are substituting this as phi. So, this quantity becomes phi, that is cos phi, and then replacing cos phi and then sin phi. So, the relationship here is now sin A minus B. We get the relation sin A minus B. It is sin A cos B minus cos A sin B. So, we are replacing it by sin A minus B, and therefore, we get the relation that sin omega n root of 1 minus zeta square into t is equal to 0. Since we are talking about the maximum value, we are differentiating the time response value and equating it to 0. So, what is the acceptable solution for this? As we had seen, the response has the first overshoot, and that is the maximum value. There is undershoot also. This is, we call it as undershoot. Yeah, this is the first overshoot, then we have one undershoot, then there is overshoot, then this is a undershoot, this is again a overshoot. So, here we are talking about the overshoot, that is the first overshoot, and since peak time corresponds to the first overshoot, we are equating this to pi, and therefore, the peak time Tp is equal to pi upon this. And the first undershoot will occur at t is equal to 2 pi upon omega root of 1 minus zeta square. Similarly, the second overshoot. So, in the response curve, this is the first overshoot, this is the first undershoot, this is the first undershoot, and the value of the first undershoot, the time when first undershoot is obtained, and the second overshoot, this is the second overshoot, and so on. We can calculate the value at what time the response curve reaches the first peak overshoot, because we are talking about the peak time. Peak time is obtained when the response curve reaches first time its maximum value, and that is denoted as Tp, and remaining undershoots and overshoots can also be calculated by giving this relation. Next is the peak overshoot. Peak overshoot is obtained as I had shown here. Yes, peak overshoot is the distance from the reference input to the maximum value, that is when the time is equal to Tp. We can see that it is maximum overshoot or the peak overshoot is when the time, the response when the time is Tp, that is the peak time minus 1, because we are talking about this distance. We are talking about this distance from here till here, because the response is obtained here, we get this value and subtract 1 out of it. So, MP, that is the peak overshoot, is 1 minus the distance, subtracting the value, then substituting the value of peak time here, substituting the value of peak time Tp in this expression, we get it as We are subtracting this value by -1. So, we have a negative sign here and substituting the value of Tp as pi upon omega n root of 1 minus zeta square as obtained previously. This is what is obtained. We are substituting its value here. So, this time is now pi upon omega n root of 1 minus zeta square, and correspondingly again substituting the value of Tp here, pi upon omega n root of 1 minus zeta square. What happens to the expression now? Here we are getting it, this quantity cancels out here, we are remaining with only pi, and here omega n cancels out, we are remaining with the value of peak overshoot. What is the response value at that time? It is this quantity. Now, we are finding the expression for the maximum peak overshoot. Again substituting the terms, root of 1 minus zeta square as sin phi and cos phi as zeta and tan phi as root of 1 minus zeta square. Substituting the quantities, we obtain the value of peak overshoot, which is equal to this value, and substituting sin phi as root of 1 minus zeta square. So, maximum peak overshoot is equal to e raised to minus pi zeta upon root of 1 minus zeta square, and this, as we know that this value is monotonically decreasing function of zeta and is independent of omega n. We do not have the term omega n in this expression, and it is an exponential term. It keeps on decreasing with respect to the peak overshoots and the peak with respect to the overshoots and the undershoots. So, this is the expression for the peak overshoot. How is settling time defined? Now, what is settling time? Settling time is that time when the response reaches its steady state value, and we can see that this expression of time response is having a sine term as well as an exponential term. So, the sine term is responsible for the oscillations and the exponential term is responsible for taking the time response towards a desired value. So, over the time the response of the curve reaches the steady state value. So, it has a sine term as well as an exponential term, and as we have already defined what is the time constant. Time constant is 1 upon zeta omega n. So, we are considering only the exponential term. Since we are looking at the settling time, we are talking about the exponential term, and that exponential term is taken for a condition with a tolerance band of 2%. As mentioned, settling time is in the definition as we had mentioned here. It is the time required for the response to reach and stay within a specified tolerance band, usually 2% or 5% of the final value. So, we are taking the acceptable part as 2%. So, here equating the part to 0.02, and therefore, this corresponds to 4 time constants. So, settling time is for a 2% tolerance, settling time is 4 time constants, and similarly it can be found out for 3%, for 3%, for 5% it is 3t, and for 2% tolerance it is 4 into time constant, and t is the time constant that is given by the relation 1 upon zeta omega n. The time domain specifications as related to delay time, rise time, settling time, peak time and the peak overshoot. When we design the control system problems, the design specifications are being specified as to how much peak overshoot is required, or how much is the limit of the peak overshoot, and what is the rise time and what is the settling time. So, based on these values, a control system is designed. So, the time domain specifications, performance indices has been discussed in this lecture. Thank you.